Hello everyone, my name is Niloofar Minbashi. I'm a PhD student at Division of Transport Planning from KTH Royal Institute of Technology of Sweden. Today I will discuss the application of machine learning in the departure prediction of freight trains from rail yards. The results that I will present today are my preliminary results that I've been working on with the supervision of my supervisor, Professor Markus Bohlin. In this presentation, I will cover 4 main points. First, I will start with the motivation and the problem definition of my research. Then I will describe the method and the position of machine learning in railway operational problems and why we chose it. And briefly, I will discuss the results that I have obtained so far, how I improved them, and what are my plans for improving my model will be described in the future direction of my presentation. Since 2015, European Union has come up with the concept of creating a single European rail area. The idea is that rail transport is an environmentally friendly mode of transport and it plays an important role in connectivity, economic growth, and decarbonization of Europe. Therefore, EU wants to go from single individual railway networks to create a connected, united railway network that covers the whole Europe. One of the first steps towards this was launching a series of big projects called Shift to Rail, which aim at improving the modal share of rail transportation. In terms of rail freight, the aim has been to reach a 30% of modal share by 2030, which is currently 18%. And to achieve this, we need to improve the reliability and punctuality of rail freight services. One of the areas that can contribute to this improvement is rail yards. Rail yards are large areas dedicated to dispatching freight trains to the network. In fact, they receive arriving trains, rearrange their rail cars, and send them to the railway network. In Swedish railways, delayed departures from the yards has been one of the 5 main causes of delays of freight trains. This is not just limited to Swedish railways. This is a more or less common issue in other European railways. Delayed departures from the yard can impact the punctuality of other freight trains on the network. And in a bigger picture, they can impact the overall punctuality of a railway network. Therefore, we need to improve the performance of rail yards in a railway network. Therefore, as a part of Shift to Rail project, some of the projects have been dedicated to the interaction between the yard and network. The aim of this project have been to analyze, study, model, and optimize the performance of the yards in the network, in a railway network. These projects are ARC, Smart, Freight Hub, OptiYard, Freight Rail 2, and Freight Rail 3. The results that I'm presenting today are a part of Freight Hub project. And what I'm going to do for the next steps of my PhD will be a part of Freight Rail 3 project. Now, if I want to clarify the problem a little bit more, I should start with the overall functioning of rail yards. Rail yards comprise of 3 sub-yards: arrival, classification, and departure. In the arrival yard, the arriving trains are received. In the classifications, the rail cars are rearranged, and in the departure, new freight trains are attached to the locomotive, and when there is capacity on the line, they are sent to the railway network. So far, most of the research has been dedicated to the improvements and optimization of classification yard, because it's the most time-consuming sub-yard and it's a bottleneck of a rail yard. But the thing is that these 3 sub-yards are interconnected and interrelated. If you want to build new models, we have to focus on a comprehensive overview over the yard and consider the interaction between these 3 sub-yards. But the problem is that finding these interrelationships between these 3 sub-yards is difficult to grasp or mathematically model. That was the reason why we chose machine learning approach, because with machine learning, we can learn from this historical data and we can indirectly consider these interactions between these three subyards. That was the reason why we chose machine learning for our problem. Now I move on to the method section of my presentation. Basically, a wide range of railway operational problems can be addressed by machine learning and the three types of learning in machine learning. Some of these problems are less complex, such as dynamic pricing. Some of them are more complex, such as predictive maintenance of the infrastructure. But the problems that are very complex are the ones that deal with the real-time management of railway networks. The problems such as disruption mitigation, real-time scheduling, journey delay prediction are very complex problems that can be dealt with reinforcement learning. Our problem, which is a departure prediction, is a sort of forecasting predicting problem that can be solved by supervised learning methods. In Swedish railways, the departures from the yards can be classified as three classes: delayed departures, on-time departures, and even early departures. Early departing is a common practice in Swedish railways in order to offset all other delays that might be encountered by the freight trains during their journey. And we started our prediction model by implementing a classification approach by which we simply classify the departing trains. And it is beneficial for the infrastructure manager to know if the departing trains will be early, on time, or delayed, and they can kind of plan for other trains on the network and how this might impact the other trains on the network. The procedure has been straightforward, like other machine learning algorithm implementations. We have a training data set, we build the algorithm, then we evaluate the algorithm based on the new data sets or on the test data set. Here I will show like more detailed schema of our modeling. There are different classification algorithms that can be used for a problem, from decision tree, random forest, k-nearest neighbors, support vector machines, and neural networks. So far we have worked on decision tree and random forests and a little bit of support vector machines. But the results on the random forest have been the best results so far. From the data set that we had, which was a small punctuality data set, we set some predictors, which comprised of arrival hour, arrival weekday, arriving train, arrival deviation of the arriving trains and wagons, which can deal with kind of the arrival yard. We had the standing time of the rail cars in the classification yard, and we also had the departure weekday, departure hour, and departing train, and which deal with the departure yard. And by that, our target was to classify the departure status of the departing trains. Now I describe the results for the random forest. As I said, it was the best results we have obtained. Our data set was a 1-month data set, which comprised of 6,243 departures. And this data was from Hallsberg Yard, which is the largest yard in Scandinavia, an important domestic yard for Swedish railways. If you want to evaluate the performance of a machine learning approach, there are different parameters for that, which are based on why and how we want to use our results. We chose recall and precision. By recall parameter, we want to evaluate how good our model is in identifying positive instances. And by precision, we want to evaluate how good our model is in assigning positive instances to the positive classes. In fact, how good our model is in assigning delayed departures to the delayed class. We can see that for the recall parameter, The results for the delayed and on-time departures is quite low. It's 24% for the delayed and 43% for the on-time. The precision of the model, however, for these two is fairly similar. It's 63% for the delayed and 68% for the on-time departures. The results for the early departures is much better. But why this has happened to our results? The idea is that early departures comprise more than 65% of our data set. And we are facing a problem which is called imbalanced data in machine learning approaches. Imbalanced data means that we have some classes that are very important for us, but they are the minority classes. So we don't have enough instances from them to predict them correctly. Imbalanced data problem can be dealt by three types of techniques: problem definition techniques, data level techniques, or algorithm level techniques. By problem definition, we redefine our evaluation parameters. By data level, we modify or manipulate our data set and our minority classes. And by algorithm level solutions, we try to modify our algorithms, the algorithms that we're using. We used a technique from data level, which is synthetic minority oversampling technique. By this technique, we oversample the instances in the minority classes, sometimes by simply duplicating them, or sometimes by oversampling them by using k-nearest neighbors, which we chose. And we can see that the results became much better for the recall parameter. Now we have a 62% of delayed departures identified correctly. But in terms of precision, the results did not change that much. Overall, our model is more than 68% of the times is good at assigning the right departing train to the right class. However, using Smooth has decreased our good performance in the early departures. This is the current status of our results, which we are working on improving it. And in the next slide, I will say how we want to improve. In this presentation, this was, I think, our first attempt to show that machine learning can be beneficial for yard departure prediction. But there are challenges towards this, at least for us in Sweden. In Swedish railways, we have the problem with data security, because yards are regarded as places that are very important in terms of security. So obtaining data for the yards is not an easy job. Another thing is that there are different data owners regarding the operations in the yard. We have the yard operator who owns the data for the classification yard, and we have the infrastructure manager who owns the data for the arrival and departure yard. So it is difficult to obtain the data from these two main stakeholders, because each of them have their own interests. But what we are going to do is to add more data, which can include more predictors. Like we can also use weather data or some other operational data. And the other step is to make a comparison, to generalize, to see if with other yard layouts we can achieve better results, or how different yards can have different results. With this slide, which shows a part of our beautiful campus, I would like to thank you for listening to my presentation. Thanks for your attention and your time. I'm available for any further idea or discussion. Thank you very much.